Okay, so like as I said last time, we will take a look at a new topic which is related to Perron-Frobenius theory. But if you have some questions on Perron-Frobenius that are not clear, you can ask now, so we can spend some time. Otherwise, I want to talk about matrices over max algebra. So I have uploaded one file actually that you can take a look at that. And I'll be using the same file in this presentation. So max algebra, the name, the basic structure, I'll first tell you, but there are many other algebraic structures which are also studied. But the basic structure has the ground set is, we may call it script M. This consists of the real numbers together with minus infinity. That is our set. And there are two binary operations, addition and multiplication. The addition, which we denote by a plus with a circle, is the maximum of A and B. That's why it is called max algebra. And the multiplication, either I write a cross or sometimes just a dot, is the usual addition. So in the beginning, you will have to get used to this because it takes time to sort of get used to the operations and how they work. But we'll see several examples. So first thing to note is minus infinity acts like an additive identity, because if you take, say, any number 5 plus minus infinity, you will get 5 because it's the maximum of 5 and minus infinity. So minus infinity is playing the role of 0 in this algebra. And 0 acts like the multiplicative identity, because if you take any number, this could be positive or negative numbers also, because we are taking real numbers. No. Okay, I might use a circle, I don't know, just to distinguish from the usual multiplication. So if we take with 0, then it is minus 7. So 0 acts like the multiplicative identity. Just keep this in mind. Minus infinity is the additive identity and 0 is the multiplicative identity. So we can have vectors over this algebra, and we can also have matrices over this algebra. And how do we define the matrix addition and multiplication? First of all, let's see the inner product. So if I have a row vector, and if I take the scalar product with another column vector, then you have to take 5 multiplied by 2 in the max algebra. And so let me write it. So 5 multiplied by 2, then max addition 3 multiplied by minus infinity plus minus 2 multiplied by 1. And so 5 multiplied by 2 is 5 plus 2, which is 7. 3 multiplied by minus infinity is minus infinity. because sum of 3 and minus infinity. And then minus 2. Please correct me if I'm, because it is very easy to make mistakes in this, because we are not used to this algebra. So please correct me if you find I may be wrong. And minus 2 multiplied by 1 is minus 1. And then we have to take the maximum of this. So that is 7. So that is the inner product of these two vectors. Okay, so once we have the inner product, I can define matrix multiplication. Okay, just 1 minute. The laptop is not charging. I'll just fix the why it is not charging. Okay, it's all right. Okay, so now we can define addition of matrices and multiplication of matrix multiplication. So I think I'll show you the file. We can go over that file. You can also simultaneously open it if you want. I hope you are able to access it. This is in the Dropbox also.
Hello, sir.
Yeah.
Sir, is this set forms a vector space in the R union minus infinity over R?
No. So it's not a vector space by the usual definition of vector space, but you can sort of introduce vector spaces like type of thing. So actually it's a very broad, very well developed theory. And so I'm going to make some general remarks about this area in general, but let me just mention one reference, which is an old reference, but that treats the basics like very slowly and algebraically. And that is this book, Cunningham Green. This will not be available in internet. I think it was an old book, 1979. It's a very nice book to read if you are a student or learned linear algebra. Then this will introduce the basics, but the notation of the book is very, very tough. I mean, you have to spend time. But he really explains the structure very well. And you can ask the usual questions. I mean, is it a vector space? What can you say about rank? What can you say about determinant? And all these linear algebra questions. And they are answered in this book. They can be done to some extent. And nowadays, it is very well developed, but the results are difficult. So you get results like rank. Rank results are very difficult. There are many results, but they are not like the usual results. And if you want a slightly lighter introduction, then that is that Butkovic, this book, Max Linear Systems. So that is a better, more modern kind of a book. Cunningham Green is a classic. I mean, it has some 20 chapters and each is full of technical details. And even now, some of those questions are not answered fully or not paid attention fully. Butkovic is a more recent introduction. And this three-author book is a introduction to applications. And now recently the area has, many different people have worked in this area from different fields. So it goes by many different, similar area goes by different names also. Like some people call it idempotent analysis. That's also the same area. Or some people call it, I mean, the Boolean algebra is a special case. So Boolean with the multiplication and those slightly different operations, but that's a special case. Then some people call it tropical geometry. That's also another. I don't know the exact reasons for all, but these are more modern names. And now the area has gone into very abstract extensions. So those are. So if you are interested from the algebra point of view, then there are many abstract structures which are more general, and people have studied those. So my goal here is very modest, just to tell you the basic introduction and then deal with the eigen problem, because the eigen problem is very similar to the Perron-Frobenius theory, and a lot of results have equivalent to them. That is my very modest objective, and there also I will not give all the proofs, but some of the proofs are contained in this short note that I have. Okay, so let's see some.
Hello, sir.
Yeah.
Sir, actually, this name algebra has nothing to do with the algebraic structure.
No, this is an algebraic
say that?
structure. This is an algebraic structure. No? Algebraic structure means an abstract set with operations. Yes, is it?
It has to be like vector space structure along
No,
with
no, no,
multiplication
no,
and
no,
divide.
no. That is not necessary. Algebra just like if you take, if you are familiar with Boolean set, that means 0 and 1 only, and 0 plus 0 is 0, and 1 plus 1 is 1, not Galois field operation. 1 plus 1 is 0. No, 1 plus 1 is 1, and 1 into 0 is 0, and 0 into 1 is 0. So that's a Boolean matrices, and that is more well known. I think you might have seen it in the truth tables and all those things. And that's a very legitimate algebraic structure. So algebraic structure has nothing to do with vector spaces. Vector space has to do with some geometry and so on. So here I definitely have an algebraic structure, you can call it. There's a set with two binary operations. So in that sense, it's an algebraic structure. Okay, so let us look at addition and multiplication of matrices. So I have two matrices here, A and B. And addition is easy because you just have to take entry wise. So 2 plus 5 in the max algebra is 5, the maximum. So you get 5. Then 1 and minus infinity is 1. Then 2 and minus infinity is 2. Then minus 1 and 0 is 0, 2 and 4. So that's a addition. Then scalar multiplication. So I'm multiplying A by a scalar 3 and the first matrix. So you get 3. So you have to take entry wise. So 3 multiplied by 2 in the max algebra. So there is 3 plus 2, which is 5. Then 3 plus 1, which is 4. Then minus infinity. So 2. Then minus infinity and 6. 3 plus 3 is 6. That is scalar multiplication. And then matrix multiplication, you have to be more careful. You have to multiply the first row vector multiplied by the first column vector here. Sorry, I have, A into B is not possible. So I have introduced one more matrix C, and then A into C I can talk about. So A into C. So let's take the first row of A, just like I calculated that inner product. You take the first row of A and multiply by the first column of C. And so you get 2 multiplied by 1 in the max algebra is 3. 1 multiplied by 2 is also 3. And then minus infinity. So the maximum is 3. That's how you get the first entry of A times C. Similarly, the other entries. Okay, now some elementary properties can be done. So matrix multiplication is associative. That requires short proof, but very simple, just writing it down. So it is a fact that matrix multiplication is associative and matrix multiplication is distributive over matrix addition. So the usual properties are true. So A multiplied by B multiplied by C, you can group them. This is the associative property. And A multiplied by B plus C is distributive property. The transpose I denote by A transpose. Now, what is the identity matrix? So the identity matrix, in the usual algebra, we put 1 on the diagonal and 0 outside the diagonal. So here we should put 0 on the diagonal because 1 is the multiplicative identity, and here we saw that 0 is the multiplicative identity. So you put 0 on the diagonal and minus infinity outside the diagonal. Then you get the identity matrix. So just to illustrate, so when you multiply any matrix by identity of the same order, you get back A, and identity multiplied by a matrix is A. Let me just illustrate this by an example. So suppose I take a 3 by 3 matrix and over the max algebra. And multiplied by the identity matrix. So the identity matrix is this. This is the identity matrix over the max algebra. And you will see that you get the same matrix, because very simple computation and you get the same matrix. So A multiplied by identity is A. For example, if you take the first row times the first column, you get 3. So I will not do all the entries, but it's very easy to see that you get the original matrix. And same thing will work if you multiply on the left. Okay, so that is the role of the identity matrix. Permutation matrix is defined like usual, that you take the identity matrix and permute the rows and columns. And the usual thing that if you take a permutation matrix and multiply it by a matrix, then you get the effect is to permute the rows as usual. And if you multiply on the right, then you will be permuting the columns. So the first thing that we do, so for example, determinant. So determinant is not very easy here because there are minus signs and there is no subtraction in max algebra. But there is a very big theory of determinant. One can, for example, people have found different ways to take care of that problem. And one is, how do we define the determinant? So we take the product, we take the even permutations and add up their products of those, and then minus the odd permutations. So why not, since we don't have, there is no problem with multiplication. So I can always multiply. So suppose I want to define, so I'm just telling you without much going into the depth, how people have attacked this problem. So suppose I want to talk about determinant of this matrix. Then what I do, I take the even permutations and take the product. So these are the even permutations. And then I take the odd permutation. I'm not writing fully, but these are the odd permutations. There are 2 more. And usually we subtract. In the determinant, the second one is subtracted from the first. That's how we get the determinant. But here, subtraction is not available. So what I do, I look at this pair of the 2 numbers. And I'll call that as the determinant because no information is lost. So something like the plus and minus, the odd and even terms, you put them together, make a pair, and call that as the determinant. This is one way of sort of developing the theory. Another way is you take all of them to be plus. That is another way. And all these things have been worked on by several mathematicians. And now the theory has got the present stature of the theory. Even I don't follow the theory anymore. So because it has gotten very, very abstract and very, very complicated. Because with this definition, you get many results. And there's a whole theory. Unfortunately, there is no good reference for the whole theory as it is developing.
How to compute this determinant?
Yeah, so I'm not computing the data. So I know how to compute these two terms, right? This thing I know how to compute. So 3 multiplied by 0 multiplied by minus infinity, that is, so I get minus infinity plus,
How are you basically corresponding to some permutation or something?
yeah. This is the, you must be aware that when you have a 3 by 3 matrix, yeah, unfortunately, students don't calculate determinant this way. They go by the row expansion. But the way I like to do 3 by 3 matrix is, this is identity permutation, that is one permutation, then this is one permutation, and this is one permutation. That is how I calculate. And then there are 3 more. This one, and this one. So those are the 6 permutations. That's how I do it. Okay. Now I don't go by row expansion. Is that clear?
Yeah.
So that's what I have done here. And then you can calculate these two numbers and put them as a pair and work with that only. So there's a whole theory that has been developed. So I'm making the general remarks, like similar about rank, when we come to later on linear independence and dependence. So you can try to imitate. So this Cunningham Green book, which was written in the 60s, has made many such attempts, but that time the theory was not that developed, but he still has got many results. But the book is difficult to read because of the many new notation and so on, but people have worked on it now. And I would not suggest this as a research topic unless you are very patient and want to work very hard, because to come to the top of the field, what is going on now, it has become very abstract, as I said. Okay, so I will just introduce the Max eigen problem, because that is closely related to Perron-Frobenius theory. Okay, now this Max algebra has many applications, dynamical. So many of these are discussed in that 3-author book, Holzder, the second reference. So dynamical systems, transportation networks, dynamic programming, machine scheduling, parallel computing, all these areas, the Max algebra comes into play, either Max algebra or some equivalent structure. Okay, linear equations, we can write down the linear equation, and there is some theory is developed, but I will not talk much about that. But the eigen problem is going to be similar. Okay, first let us see some examples. So the idea is that you have some system or some equation which is not linear in the usual algebra. As you know, linear equations are easy to handle in general in the usual algebra, but sometimes the equation may not be linear, so that you can convert into linear if we go to Max algebra. So consider this problem. There are 2 cities A and B, and they connect to a capital city, let's say C. And from A to C and from B to C, we know the flight times, say T1 and T2. From A to C, it takes T1 time, B to C, T2 time. And some international flight is going to depart from C, and that departure time is small b. But there will be passengers coming from A as well as from B. So how should we schedule the flights from A and B so that they will catch the flight from C in time? So if x1 is the departure time from A to C and x2 is the departure time from B to C, then the total, if we start from x1, if we start from A at time x1, then we will reach C at this time, because if we start at x1 and then t1 it takes to go to C, so x1 plus t1 is the time at which we will reach C. Similarly, x2 plus t2 is the time we will reach C from B. And the maximum of those two should be at B only, because the passengers from A may arrive early, that doesn't matter, but they should wait for the passengers from B. So finally, the maximum of those two should be B. And this can be written conveniently as a linear equation in Max algebra, because T1 max multiplied by x1 plus T2 max multiplied by x2 is equal to B. So this system is linear. This equation is linear. So then we can use theory of linear equations, not in the usual algebra, but in the max algebra to proceed with this problem. That is why scheduling problems. I am giving some basic examples. So several constraints of this nature can be represented by a system of simultaneous linear equations. Okay, one more example. This you may call as machine scheduling problem. Some Markov chain type of problem. So there are n states of a system. A player enters the system in a certain state, then moves from state to state like a Markov chain at each time point, and after n moves, stops at a certain state. I don't know whether this n and this n is the same, but maybe not. That maybe you can correct it. There's a reward. There's a reward Aij for each of this transition. That means if he starts in A and goes to J, then there's a reward Aij. So there's a reward Ci in the initial state also. And there's a reward Dj in the terminal state also. So what is happening? Suppose a player starts in state I, then he immediately gets a reward Ci. Then he goes to J, he gets a reward Aij, and then a terminal reward Dj. So the total reward he gets for this transition is Ci plus Aij plus Dj. And the maximum reward is the maximum over all this over Ij. So what is the maximum reward that anybody can get? And this can be written as a matrix multiplication, a vector C dash C transpose multiplied by A multiplied by B, that is equal to this maximum. So again, we have converted. By the way, if there are n transitions, I said that this number of transitions is probably not same as the number of states. It doesn't matter. So if there are n transitions like matrix multiplication in the usual algebra, this will be the second power, third power of A. So ultimately it will be the nth power in the max algebra. So you get this compact expression where A to the power n is A multiplied by A n times. So let me tell you again what is the problem. There are n transitions, and what is the total maximum reward that all of them get? What is the maximum? And that is given by this matrix product. So this is sometimes known as deterministic Markov process because there is no probability involved, and they arise in operations research, mathematical economics, optimal control. And that is where one finds max algebra quite useful. Okay, the next example is this machine scheduling problem. So we have a manufacturing process having 3 machines, and the operations are not independent. That means the output of the first machine may be required for the second and third machine and so on. Each individual machine that runs in cycles, and a cycle of any machine can begin only after the previous cycle of the other machines is over and a certain waiting time has elapsed. And that information is summarized in a matrix. So what is the interpretation of this matrix? So the K plus first cycle, look at the first row. This shows the dependence of the cycles of machine 1 on the other machines. So the K plus first cycle of machine 1 can begin after the kth cycle of the same machine is over and 1 hour has passed, because it takes time for restarting or something. So the previous cycle of the first machine should be over and 1 hour should have passed. Also, the K plus first cycle can begin when the previous cycle of machine 2 is over and 4 hours is the waiting time for that. And similarly, the previous cycle of the third machine is over and 2 hours have passed. Similarly for second and third machine. So suppose X denotes the starting times. So the question is, how should we put the machines in operation so that the successive cycles of the different machines are sort of they are synchronized. that means the second machine and third machine, their successive cycles should be sort of will start at the same interval. So suppose X denotes the starting time of the initial cycle of all the machines. That means I will put the first machine, start it at time x1, second start it at x2, and third at x3. Then A max algebra product X will be the time when the second cycle of the three machines can start. A squared multiplied by X will denote the starting time in the successive cycles because of the interpretation of matrix multiplication. And if we want this to be synchronized, then we want A multiplied by X should be some lambda multiplied by X for some lambda. What will happen then? That the successive cycles of the first, second, and third machine can begin after the same time interval lambda. So we can sort of make this automatic. We can set the machines in motion and have a waiting period lambda. So successive cycles of all the machines will be separated by the same time interval, resulting in a smooth operation. And if you look at this equation, it is nothing but the eigenvalue eigenvector equation. So that is why the eigen problem is coming into play. So the A into X is lambda into X, which is precisely the eigenvalue eigenvector equation over the max algebra. That's how eigen problem is coming in the picture. Okay, so these examples are very elementary, but you can find more involved examples in those references. Okay, now this matrices and graphs is very similar to our non-negative matrices. So let me just make one remark that if we take this basic algebra that we have, and if we make the transformation, so we have the set R union minus infinity. But if I use the operation X going to e to the power X, then this will go to non-negative numbers because minus infinity will go to 0, e to the minus infinity, and all the other real numbers will go to some positive numbers. So we get 0 to infinity, we get non-negative numbers. And then we can take the two up. So now we can have the ground set as the non-negative numbers, and we can have, let me just call it tilde as again maximum. There is no change here, but the multiplication is the usual multiplication. That is because e to the power a plus b is e to the a multiplied by e to the b. So if you consider this is an equivalent algebraic system, there is not much difference between this system and this system. And this system, so classically max algebra means this system, but you can also deal with this system. And here it resembles non-negative matrices. And so, for example, when I want to write the graph associated with a matrix over the max algebra, I'll essentially take this non-negative matrix. So, and then exactly the way we have defined graph in the Perron-Frobenius series, same way. So, suppose I have a matrix over the max algebra. So keep this system in mind, but I will not talk about this system today because it will confuse you unnecessarily. But these are equivalent. So here it resembles non-negative matrices much more. Not to say that the theory becomes any easier, but it becomes much more similar to non-negative matrices. Okay, so suppose we have a matrix over the max algebra, and how do we define the graph? Now here I take the usual graph as we do earlier, but you can also think of take e to the power entry-wise, e to the power exponential, and take the usual graph the way we have defined it. So there will be 3 vertices. And now we will consider the weighted graph. That means I'll have a loop at 1, and there will be a weight of 3 because the 1 entry is 3. Then I'll have a edge from 1 to 2, and it will have a weight of 2, and so on. So I'm not completing it, but and if it is minus infinity, then that is like 0. So 1 to 3 there is no edge because the entry is minus infinity. So as in the usual case, if you take e to the minus infinity, you get 0, and then we don't have an edge. Similarly, 2 to 1 there is no edge. 2 to 2 there is a loop of weight 0, and so on. 2 to 3 there is a edge of weight 1. Okay, I will not complete it. And or let me complete because there are only 2 more entries. So 3 to 1 there is an edge of weight 1. 3 to 2 there is no edge, but 3 to 3 there is a loop of weight 1. So that is the matrix associated with, that is the graph associated with this matrix. And then we can define a matrix to be irreducible over the Max algebra if the corresponding graph is strongly connected, as usual. And we say that a matrix is otherwise we say matrix is reducible. And also, if the underlying undirected graph is not is connected, and like the way we did for non-negative matrices, that also we can talk about over Max algebra. So irreducible matrix, we have the similar definition that a matrix over the Max algebra is said to be irreducible if this graph is strongly connected. And I'll concentrate on the eigen problem for irreducible matrices. When you go to irreducible matrix, when you go to reducible matrices, even for irreducible matrices, the theory looks like the usual theory, but there are some differences, many differences, and but it is highly developed. And when you go to, so it is there in the literature. And when you go to reducible matrices also, people have studied it very well. So let us look at eigen problem for irreducible matrix. I think here I have some small results. I will not talk much about that. Okay. I mean, I will state without proof maybe. So as usual, the graph is strongly connected. If there's a directed path from I to J, that is for the graph, and then graph is connected, that means you don't get this kind of situation. This is not strongly connected, just connected. And G is strongly connected if the usual definition we had. Minus infinity plays the role of the zero matrix here. So graph is strongly connected. If and only if there's no permutation matrix P such that this happens, where A11 and A22 are square matrices. And the same definitions as before. Okay, so here I am again explaining the transformation. Okay, now so we have the weighted directed graph, and like last time we have circuits. We have circuits. We may have circuit. Any loop is also a circuit of length 1, or in general you may have circuits of some length. Here you have a circuit, for example, 3 goes to 1, 1 goes to 2, and 2 goes to 3. That's a circuit of length 3. And the loops are circuits of length 1. I don't think there's a, yeah, so these are the circuits in this graph. And what we will do is, I will take the sum of the elements. So a length of a circuit is the number of edges as usual, and a loop is a circuit of length 1. So what I want to do is, I want to take the sum of the elements in the circuit, sum of the edges in the circuit, and take the and divide. So take the mean. So okay, by the way, the matrix multiplication, we have already seen this, but this works as usual, that the matrix multiplication has this interpretation, power, and that is why, so as exactly as in Perron-Frobenius theory, that the ij element of A squared, for example, A squared is the Max algebra, in the Max algebra. So the ij element of A squared will be the maximum length of a path, maximum weight of a path of length 2 from I to j. And that is illustrated because of this definition of matrix multiplication. And similarly, the ij element of a to the power n is the maximum weight. The maximum is coming because that is like addition. In the usual algebra, if we take the weighted graph, I did not mention it, but you can take the weighted graph in the usual Perron-Frobenius theory, and we just talked about the ij element of a to the n being positive or 0, and we said that it is positive if there is a path of certain length and so on. But what is the actual entry? So the ij element of a to the n is nothing but the sum of the weights. You have to take the sum of the weights of the paths from I to j of length n. And here in max algebra, the sum is the maximum. That is why you are getting the maximum weight. Okay, so as in the usual Perron-Frobenius theory, here also the powers become very important, interpretation of powers. And I can define an equivalence relation, but I will not require this much because we are going to consider only irreducible matrices. So we will say that, but let me just introduce this. So we will say that two vertices are equivalent if they are I equal to j, or there is a path from I to j and a path from j to I. So the access property, what we were talking about. And suppose v1, v2, vk. So in a strongly connected graph, every vertex is equivalent to every other vertex because there's a path from every vertex to every other vertex. In general, we can divide it into equivalence classes. So I and j are equivalent if I is equal to j, or there is a path from I to j and j to I. And suppose v1, v2, vk are the equivalent classes. And these are in the graph theory language, these are sometimes called the strong components, like the usual components. And we say that vk has access to vi if there is a path from some vertex in vk to some vertex in vl. Then we say that vk has access to vl. Okay, so suppose G is the graph associated with the matrix A, then I think I skipped. So this is the okay. And this is similar, the Frobenius normal form, the same thing that I introduced last time. The matrix is reducible, then we can do this operation and get the Frobenius normal form. The same idea as before. In other words, you take the e to the power, the entry-wise exponential, and use the usual, that becomes a non-negative matrix, and then use the usual Frobenius form. That's what it is. Okay, now let us look at the eigen problem, and I want to explain properly the eigen problem for an irreducible matrix, because the general eigen problem, then one gets into the usual technicalities. Maybe I'll mention towards the end, like last time I mentioned this homework problem. I think I should talk about it a little more, because which eigenvalues have a non-negative eigenvector, I was saying something last time. But that is when we come to reducible matrices. Okay, so now let me concentrate on irreducible matrix. And so let us look at an elementary eigen problem. So let's take a 2 by 2 matrix. 2 minus infinity, that is the first row, and 1, 3, that is the second row. And if I multiply this by minus infinity is 0. By the way, this matrix is reducible. So, but I am taking just as an example. So if you multiply this by the vector minus infinity is 0, then you can carry out the multiplication, and you will see that you get minus infinity 3, which is 3 multiplied scalar multiplication minus infinity 0. So 3 is an eigenvalue with the eigenvector minus infinity 0. And just to talk about that machine scheduling example, which we had 3 machines and so on, you can see that 1, 0, this is the same matrix. So 3 machines in that example. So 3 machines, and these are the dependencies of the cycles. Then you can check that this 103 is an eigenvector with eigenvalue 4. So what is the interpretation of this? That this tells you how to start the machines. So you start the first machine. So actually this is the second component is 0. So start machine 2 right away. Suppose machine 2 starts first. Then after 1 hour, you start machine 1. And after 3 hours, you start machine 3. So if you start that way, then because the eigen problem has that as an eigenvector, it will so happen that the successive cycles, they will be separated by the common time span of 4 hours. Exactly 4 hours. So you don't have to worry about how the cycles will start after that, because the constraint was that the first cycle of the first machine will start after the previous cycle and 1 hour has passed and so on. But that will be satisfied because we have solved the eigenvalue eigenvector equation. So let me repeat. You start the second machine at the right in the beginning. After 1 hour, start the first machine. After 3 hours, start the third machine. Then the second cycle of all the machines will start after 4 hours. The third cycle of all the machines will start after 4 hours after that. So they are synchronized. So I just gave an illustration of how that max eigenvalue problem helps there. Okay, now there are simple observations about eigenvalues, but I will not go much into that because now I'll go to irreducible matrix only. Okay, I may come back to this once I'm done with the irreducible if it is possible. Okay, now in the theory of Perron-Frobenius theory, the I plus A raised to n minus 1, that matrix was playing an important role. And the same role is played here by this matrix which we are calling gamma of A. So take gamma of A as the max sum of A squared up to A to the power n. By the way, if you have a graph of n vertices, I think sometime back I mentioned, which is wrong, that the path can be of length n minus 1 only, but that is not true. It can be of length n also. Like if you take this matrix, just a cycle, then so there is a path from 1 to 1 of length 3. So but if you go beyond 3, then it will contain a cycle. So you can omit the cycle. So in a strongly connected graph, from any vertex I to any vertex j, there is a path, and a path will have length at most n. If I is not equal to j, then the length will be at most n minus 1. But if I is equal to j, then the length can be n. Okay, so that's why we are taking up to a to the power n. And so first of all, in the case of Perron-Frobenius theory, we saw that I plus A raised to n minus 1 is a strictly positive matrix if A is irreducible. Similarly here, this gamma A matrix, what is the meaning of strictly positive in Max algebra? Strictly positive means finite, because minus infinity is playing the role of 0. So so gamma A has no minus infinity. And that's a fact because from any vertex to any other vertex, there is a path of length at most n. And so all the elements, so if you take the ij element of gamma A, that is as we saw the interpretation earlier, the ij element of gamma A is the maximum weight of a path from I to j. And the length of the path can be at most n. And so it will be captured in the right hand side because A is telling you the paths of length 1, A squared is giving you the paths of length 2, and so on. And so gamma A ij is equal to the maximum weight of a path from I to j. And so gamma A has no entry equal to minus infinity. And so gamma A is an analog of a strictly positive matrix. I'm just giving you the parallels with Perron-Frobenius theory. Okay, in Perron-Frobenius theory, we had a result that if a matrix is irreducible and if you have a non-negative eigenvector, then it is positive. So similarly here, if A is irreducible and if X is an eigenvector, then all the entries must be finite. All the entries must be finite, that is the analog of strictly positive, as we just saw. And that can be proved very similar to the earlier proof. So there's a short proof. Okay, now we take a circuit in the graph and we take the weights and we take the usual arithmetic mean of those weights. Sometimes it is called a circuit geometric mean. Actually, the term geometric mean comes because the sum is nothing but the product over the max algebra. So we may call it a geometric mean. So if tau is a circuit, then PA tau will denote the corresponding circuit geometric mean. So we take a circuit, we take the usual arithmetic mean of the weights, and then that is called a circuit geometric mean for the circuit. And then we look at the maximum over all such circuits, and that we call as mu of A. And this mu of A, actually this is a very interesting and surprising result, that this plays the role of the Perron eigenvalue. So I want to explain why that is true. But here is one example. So consider this matrix, 3 by 3 matrix. Here is the graph associated with that matrix. So 1 to, there's a loop at 1 of length 1, of weight 1, then 1 to 5 weight 2, and so on. 2 to 2 there is no loop because the 2 to entry is minus infinity. This is the matrix. Now what are the possible circuits in this and what are the corresponding geometric means? So let us write them down. So for example, 1 to 1, that's a circuit, 1 to 2, 2 to 1, that's a circuit, and so on. And then 1 to 2, 2 to 3, 3 to 1 is a circuit. So in this table, I have given all the circuits. These are all the circuits and in that graph. And if a circuit is tau, this is the corresponding geometric mean. That means the arithmetic mean in the usual algebra. And here the maximum is 6. So the main theorem here is, this is quite in contrast to the Perron-Frobenius theory, that an irreducible matrix has only one eigenvalue. Okay, it has only one eigenvalue. The usual kind of n eigenvalue is no longer true. And that one eigenvalue is nothing but the maximum of the circuit geometric mean. So it is mu A. So if you take this particular matrix, it has only one eigenvalue in the max algebra, and that eigenvalue is 6. So this is quite in sharp contrast with the usual Perron-Frobenius theory. Okay, so let's try to understand why it is happening. So let's take an irreducible matrix and let us look at the eigenvalue-eigenvector equation. So lambda is some eigenvalue with x as the eigenvector. And because A is irreducible, all the coordinates of x are finite. There is no minus infinity as far as x is concerned. So if you rewrite this linear equation in terms of using the definition, what you have is, because if you take the inner product of the ith row of A times x, you get the maximum of Aij plus xj over j. This is the usual product over the max algebra, and that should be equal to lambda plus xi, the right hand side, lambda plus xi. So this becomes the system that we are trying to solve. This is true for all I. Okay, so what this system means is that Aij plus xj, first of all, it should be, the maximum should be lambda plus xi. That means ai plus xj should be less than or equal to lambda plus xi. So I'm rewriting as ai plus xj minus xi less than or equal to lambda. But that is not the only thing, because this will only ensure that the maximum is less than lambda, less than or equal to lambda plus xi. But I want equality. So for that, I should insist that for every I, equality holds for some j. That is an additional requirement. Then only you will get the maximum equal to lambda plus xi. So what we are trying to solve here is a system of inequalities, and where there is this additional constraint that for every I, there should be some j for which equality holds. And you might have observed that this is becoming similar to some linear programming constraints. And in fact, there is a simple relation with this max eigen problem. Has a relation with, it can be solved by linear programming, because we are getting this system of linear inequality. Okay. So first I want to show that any circuit geometric mean in the graph will be less than or equal to lambda, if lambda is an eigenvalue. So I want to show two things. One is that lambda is equal to mu a, that is the only eigenvalue. And here I am trying to show that any other circuit so I want to show first of all that the maximum circuit geometric mean is less than or equal to lambda. And it is less than or equal to lambda because, so this inequality is, if you look at, if you now take a circuit and apply this to every element in the circuit. So if I take I1, I2, I2, I3, dot, 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 Ik, I1, and for each of these I apply this inequality and add those inequalities, then what will happen? Because it's a circuit, the x part will cancel out, because you will get xi1 minus xi2, but in the next equation it will be xi2 minus xi3. So xi2 is cancelling. So like that, x part will cancel. So I am taking this inequality for each of these elements in the circuit and adding them, and then you can then divide by the circuit length, and then you will get the circuit geometric mean is less than or equal to lambda, and that is what we are calling as mu a. And because this is true for any circuit, so the maximum circuit geometric mean is less than or equal to lambda. And now I claim that in fact equality holds. So I think I'm going a little fast, so let me go back. What I'm saying here is, so let us go back to the eigen problem. Then it is equivalent to this system, where with the additional constraint that for every I there is a j for which equality holds. And then I have said that if you take a circuit and look at these inequalities, you will get that the circuit geometric mean is less than or equal to lambda. And because this works for any circuit, we have the maximum less than or equal to lambda. But why is the maximum equal to lambda? So let us look at those ij for which equality holds here. And among those, I want to, so suppose I collect all the, look at any edge I to j, this inequality may be strict or may not be strict. So you look at all those edges where it is strict, that's a subgraph, and that I'm calling as H. So H is the subgraph formed by the edges for which equality holds. Actually, here there is a mistake, it should be in 7, equality holds in 7. Not in 6, but in 7. Now, in H, what was that condition? For every I, there is a j for which equality holds. That means in this subgraph, the out degree of every vertex is at least 1. Because for any I, there is a j for which equality holds. That means in this subgraph, H has the property that the out degree of every vertex is at least 1. So if you have a directed graph, in which the out degree of every vertex is positive, then such a graph must have a circuit. Because you start at vertex 1, out degree is at least positive, so you go to that vertex. Again, the out degree is positive, non-zero, so go to that vertex. So if you keep on doing that, you will get a circuit. So the H has that property that the out degree of any vertex is not zero. And so H has a circuit. And once H has a circuit, that has the property that equality holds. So for that particular circuit, the circuit geometric mean will be equal to lambda. And that is why mu of A is equal to lambda. Okay, so what is the conclusion? That the eigenvalue, the eigenvalue is the maximum circuit geometric mean is an eigenvalue. And now I claim that that is the only, if A is irreducible. Actually, we have also proved that mu A is the only eigenvalue because we started with a general eigenvalue eigenvector equation and then we concluded. So this is a very general eigenvalue eigenvector equation, and I concluded that the eigenvalue is equal to mu A. So it turns out that mu A is the only eigenvalue. So an irreducible matrix, the maximum circuit geometric mean is the only eigenvalue of the matrix. Okay, now what about the eigenvectors? So I think I will not give the complete proof, but if you recall that gamma A matrix, so gamma A was the max algebra sum of A squared dot 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 A to the n. So if you multiply both sides by A on the left, then you will get A multiplied by gamma A.
And mu is only eigenvalue of A.
Excuse me? Is there a question? Any question? Okay, so multiply both sides by A, then you get A multiplied by gamma A is A squared plus A to the n plus 1. And that is nothing but, if you look at the right hand side, that can be, okay, I'm not going to give a proof here, so let me go to that. So any column of gamma of A acts like, yeah, so suppose the maximum circuit geometric mean, so just like we, in Perron-Frobenius theory, we can always assume that the Perron root is equal to 1. That we did by normalizing. Okay, similarly here, I can assume that the maximum circuit geometric mean is 0. I'll give an example why we can do that. So suppose the maximum circuit geometric mean is 0, then from this equation, you are getting this equation. I'm omitting some proof here, but you get this equation, and that means any column of gamma A is an eigenvector. And if actually that column, that vertex should be on a, so what is a critical circuit? A critical circuit means a circuit where you get the maximum geometric mean. Then it is not unique because you may have two kind of disjoint circuits, both may be critical. So there are many there can be many critical circuits, but if you take a vertex on the critical circuit J and look at the corresponding column of gamma A, that is an eigenvector. For that eigenvalue 0, we have normalized it. Okay, if the eigenvalue is not 0, we can subtract. This is the analog of dividing. This is the analog of dividing a matrix to make it stochastic, and then you can assume that the largest eigenvalue, Perron eigenvalue, is 1. Similarly, here we subtract mu A, then this new matrix B, the maximum circuit geometric mean will be 0. And then we can work out gamma B, and then that will be, then look at columns of gamma B corresponding to a critical circuit, and those will be the eigenvectors. So here is one example. So A is the matrix, I think it was given earlier. Yeah, I don't know. I think it was the same. Yeah, this matrix. And suppose I want to, so here are the, we already saw that the maximum circuit geometric mean is 6. And so 6 is an eigenvalue. 6 is the only eigenvalue. And what are the corresponding eigenvectors? So what is the critical circuit here? Here there is only one critical circuit, namely this circuit, 1 to 2, 2 to 3, 3 to 1. So all the vertices are on the critical circuit. So what I'll do is I'll go to first I'll normalize, and normalization means subtracting the peron or subtracting the eigenvalue. So I'll go to Aij minus 6. Why 6? Because 6 is the maximum circuit geometric mean. So if you subtract 6 from each element, you get this matrix B. This is the usual subtraction. And now any eigenvector of B corresponding to now the max circuit geometric mean will be 0. That happens at this circuit, the minus 1, 0, 1. This is the circuit, same circuit, 1 to 2, 2 to 3, 3 to 1. The circuit geometric mean is 0. That is the maximum. You can see that any other circuit geometric mean will be less than or equal to 0. So 0 is the maximum. And for eigenvector corresponding to 0, I should look at gamma of B. So we work out B squared. You can check this later on. B squared is nothing but the matrix multiplied by itself. And you get this matrix. And then B cubed turns out to be this matrix. You can stop at 3 because n is equal to 3. And then the gamma matrix is the sum of those 3. So this is the gamma matrix. So what happens, and this requires a proof, but so any column, because all the there's only one critical circuit, and the critical circuit is the full cycle. So all the vertices 1, 2, and 3 are on a critical circuit. So any column of gamma of B is going to be an eigenvector. And you can check, for example, if I take the first column, it is an eigenvector for the circuit geometry. And you can see that the other columns are dependent on the first column in max algebra. Because if I take the first column and subtract 1, I get the second column. Subtraction is the analog of scalar multiple here in some sense. So linear dependence, independence of max algebra, actually linear can be defined as usual. That means you can say that a set of columns is linearly dependent if there's a linear combination over the max algebra, which is not trivial, and it is equal to 0, and so on. So so it will always happen that if you take a critical circuit, then any two columns will be linearly dependent. But it doesn't mean that, unlike in Perron-Frobenius theory, eigenvector is not at all unique. In fact, if you talk about the dimension, I have not defined dimension, but how many linearly independent eigenvectors are there, that will depend on the number of critical circuits, because critical circuits can be more than one. I think the kind of example that one can give is that I had this some time back, that you can have this kind of a graph. There can be one cycle here, and there can be another cycle here. I'm not putting the weights. Suppose all the weights are equal, it doesn't matter. Then this will have, this is a strongly connected graph. And no matter what weight, but just make sure that the two circuit geometric means are equal. So suppose I put 2, or let me just put all of them to be equal, doesn't matter. So here there will be two critical circuits, and both will be critical. And so you will get, in some sense, that many linearly independent, I have not defined properly linear independent, but that many eigenvectors. So it depends. So this eigen problem is well analyzed. And so any two columns of gamma B are scalar multiples over the max algebra. And if two vertices on the same critical circuit, then they are proportional. Proportional in max algebra. That means one is obtained from the other by subtracting some constant. And so you get some idea about how many eigenvectors are there. That is the number of critical circuits. Okay, about reducible matrices, I'll just make some remarks. The last time I was talking about this problem. So reducible matrix is the same thing. One can put it in Frobenius normal form over the max algebra. And I talked about the Frobenius victory theorem. So there is similar, the same kind of theorem holds over max algebra. So I think I want to now go back to that example and discuss that, because I think it was not very clear from what I observed in your session yesterday, that let me put on that file, which was this the second tutorial, the tutorial last time. So I don't know how to get out of this. Go back to the desktop. Because if I press escape, then I think the Zoom will also go perhaps. I'm not sure. So I want to remove this. Okay, so I want to, yeah, I was interested in this tutorial sheet 3. So maybe I download it again. Yeah, so I was talking about this problem. And I think some of you, I think I want to, first of all, this is an upper triangular matrix. So, and in my Frobenius normal form, I am dealing with lower triangular. So there is some confusion because of that, I think, because you have to reduce this. So the two results are similar, but one has to be careful. So let me just talk about this example in somewhat detail. And then there's a similar example over max algebra. That means if you take a reducible matrix over the max algebra, then what are the, which eigenvalues have corresponding non-negative eigenvector means finite eigenvector. Okay, so let us look, go back, return to this example. So I think I'm not talking of max algebra now. This is just the usual Perron-Frobenius theory. Look at this so I'm trying to solve this problem. Determine the eigenvalues which have a non-negative eigenvector. So the eigenvalues are all the diagonal elements 6, 2, 5, 3, and 4, but not all of them have non-negative eigenvector, because I think I thought that if you take 1, 0, 0, then 0, 1, 0, I think there was a, some of you have a feeling that maybe these are eigenvectors, but they're not. So it is all right when you come to the first yeah, I don't know where that file has gone. So yeah, tutorial sheet. Okay. So if you take 1, 0, 0, 0, that will be an eigenvector for the eigenvalue 6. But 0, 1, 0, 0 will not be an eigenvector. So here the only eigenvalues which have a non-negative eigenvector are 6 and 5. And for that, you have to look at the access properties. So why 5 is an eigenvalue? Because the third vertex, so first vertex does not have access from anywhere, because the below the entry 6 you have all zeros. That is fine. The second vertex also doesn't have the third. Okay, second vertex will have. So whenever there is access, that particular entry should be greater than that diagonal entry. So I think I think this I worked out a 2 by 2 example, and from there also you can deduce this. But I suggest that I am making the claim that 6 and 5 are the only eigenvalues with a non-negative eigenvector, and that is because of the underlying graph. That so you find out which vertices have access to 1, which vertices have access to 2, and so on, access to the second vertex. So first vertex has access to the second vertex, and because that this element is non-zero, then and this element 6 is bigger than 2. That is what causes the problem. So because this entry is bigger than 2, 2 is not an eigenvalue having a non-negative eigenvector. The third vertex doesn't have access from anybody because the other entries are 0. So 5 is an eigen, you can work out, and here of course 0, 0, 1, 0, 0 will be an eigenvector corresponding to the eigenvalue 5, but that is happening only because the zeros are present. In general, no. Then if you go to 3, then again the first vertex has access to 3, but this is greater than 3, so that is why 3 is not such an eigenvalue and 4 is also not such an eigenvalue. So if you work out the corresponding graph, and this can also be done by the eigenvector equation. Okay, so about Max algebra, I can say that you can see these references. Also, the rank over Max algebra is a well-studied topic, and there are many different kinds of rank one can define. Even for so one can define using linear dependence, one can define using the determinant over Max algebra, and then some of these ranks are going to be equivalent. I mean, they will be equal, but in general they will not be equal. I think if you even if you take a Boolean matrix, then also one can define a rank. So I think I'll just give a final example of a Boolean matrix. So a Boolean matrix, as I said, is a matrix where the elements are 0 and 1, and we take 1 plus 1 equal to 1. That's a Boolean matrix. So if you take a Boolean matrix, then this is a special case of Max algebra where we take the other model which I was talking about by making it exponential. So if you take a Boolean matrix, then there is nothing like row space and column space, but you can define, you can take linear combinations of rows and you will get a finite set. If you take all possible linear combinations, like suppose I take the first column plus the, first row plus the second row, I get 1, 1, 1, 1. And if I take the first and the third, I get 1, 1, 1, 0. So these are the vectors, row vectors I get. If I here linear combination only means, excuse me. Okay, first row plus the third row, I get this. Only I have to take sum because linear coefficients will be 0 and 1 only. Then if I take the second row and the third row, I get 1, 1, 1, 1. That's the same as the first one, so I will not write it. And so these are all the linear combinations. So there are two, you can say that this is kind of row space, and that consists of two vectors. Now, if I go to columns, if I take the first column and the second column, I get 1, 1, 1. First column and the third column, I get 1, 1, 1. So I will not write it. First column and the fourth column, I get 0, 1, 1. Then the second column and the third column, I get 1, 0, 1, and so on. Then 1, 1, 1, and then 1, 1, 1. Okay, so I think I forgot to write one thing here, that if I take the second row by itself, I get 1, 0, 0, 1. And the first row by itself, that's also a linear combination. So I get 0, 1, 1, 0. And these are the other linear combinations. And this will have, so these are the fourth column by itself. Okay. So here is a very surprising result, that the number of vectors, so this is like a column space. It's a finite space. And this is like a row space. And you will see that the row space and column space have same cardinality. It's a fact. It's a fact in general. This is the analog of row and column rank being equal. You can try with a bigger example. And the proof is possible, not very difficult, but it's a good exercise that for a Boolean matrix, the row space and the column space both have the same number of elements. So that's something like a rank for a Boolean matrix. So similarly, there are a number of such results over max algebra. This is a special case of max algebra, but there are quite a few results and some of them are very difficult to prove. And you will find even in the linear algebra journals, you will find 1 or 2 papers if you try to search under rank over max algebra. It's a difficult area, but if you are interested in matrices and graphs, then there's no harm in trying those problems. There are many open problems, but the other part is very abstract. Between the for the abstract, there are some other books which deal with the abstract theory in greater depth, and that is more difficult. Okay, so I think I'm done with, unless there are some questions. Okay, so yeah, let me just see.
So,
Thank you, sir.
Okay,
sir, we thank now Professor Ravinder Bapat for the interesting and informative lectures on dated 13, 14, 16 and today. He talked on non-negative matrices, Frobenius theory, and today on max algebra. It was a nice experience for all of us to learn from the master of the subject. We again thank him for finding the time to interact with us. Thank you, sir.
okay, thank you.